we're going to start off with a fast Fourier transform. And we're going to play around with a function, just a Gaussian. And by the way, its Fourier transform is another Gaussian. And here is your Fourier transform from a Fourier transform lookup table. If you're an electrical engineer, in the back of any good book you pick up, there'll be like, I don't know, 15, 20 Fourier transform pairs. Easy functions that you can actually do the Fourier transform for. Okay, so if you have specific forms, you get nice things. But the Gaussian is probably the most famous of them all, because the time bandwidth product is minimized. What the time bandwidth product is the width in this here, the width of the pulse here, the width of the pulse here. Take that product. A Gaussian minimizes that. Okay, so that's a trivial fact to know. But what we're going to do is we're going to play with this. We're going to try to take this function, Fourier transform it, and see what we get. Okay, as a simple warm-up demo. All right. So here we go. Lights down, and make sure that if the camera's there, it should be on the screen, I think, right? So let's pull this up here. All right, here we go. So, and there's some very interesting things you have to know about the Fourier transform. So I want to make sure we cover them so you know how this thing works. So first of all, let's take this function. Let's define it on domain. Let's make it domain size 20. Okay? And what I'm going to do is pick a number of points to discretize this with. And this ultimately turns out to be then how many Fourier modes I use. I should pick a power of 2. 128. Okay? Remember the FFT routine to get n log n. Takes this problem, splits it into 2, splits it into 2, splits it into 2, all the way to n 1 by 1s. Okay? And then I make a domain. Let's call this x2 for a moment here. And what x2 is going to be our domain. It's going to be a linear space that goes from negative L over 2 to L over 2 in n plus 1 points. Now, why n plus 1 points? The first point is the last point. So I'm going to have total n points that I want to keep track of, but the last one is really the first one, so I don't need to keep track of it, right? But it's still one of the points. So when I discretize this domain, I have n intervals, but n plus 1 points. Okay? And so I only want to keep the first 1 through n of them. So I just say, go grab the first 1 through n points. There's my x values. Okay? I'm already setting up the fact that I know it's going to be periodic. All right. Got that. Now let's define a function. Here's the Gaussian. And then we just plot it. So I made a Gaussian, I plotted it, and let's look at it. And come on over here. There it is. Woohoo! All right, we got a Gaussian. I'm going to Fourier transform that, and I should get a Gaussian. Okay? Ready to Fourier transform? Let's call UT our Fourier transform. You go FFTU. That's it? Nice, huh? All right. Let's plot that Fourier transform. UT. Huh. That look like a Gaussian to you? All right, so what went wrong or what went right? So FFTU gave us this. And this is where it's important to realize that the thing that kind of went on here is that when you look at this function, it doesn't look like a Gaussian. But what the FFT does, remember, it's trying to solve this thing at n log n speed by breaking it up to smaller and smaller problems. And the way it breaks it up is it takes this problem and it does a butterfly algorithm. I'm going to talk about it later. And it flips the domain. So this side went over here. This side went over there. And it multiplied every other component by -1. This is part of the algorithm. Why doesn't it undo it? for you, right? Because why would it leave it like this? The reason it doesn't undo it for you because it costs effort. The whole point is it's trying to be fast. Why should it be slow on your account? Right? I mean, that's ultimately what it is. It's trying to go fast. And by going, the best thing to go fast is to do this, work it, and don't undo it until you absolutely have to. Okay? Now, if we wanted to plot this thing, though, in the Fourier domain, we could just say, okay, how about we do the following? First, I want to unshift it then, because it's shifted, and there's a nice command. Let's call it UTT. It's actually, I'll just do this. FFT shift. Okay? And it knows to shift it. It shifted it. By the way, still has that multiplication by -1 problem in there. So you could always say, well, okay, look, this thing's fine. I'll just take the absolute value of this thing. Or I can multiply every other one by -1, but right now I'm lazy. And I can just do that. Boom! Gaussian. Sweet. I got 2 Gaussians. All right? Everybody good with that? Okay. Gaussian goes to Gaussian. You just have to know how to pre-process. And, by the way, you better know that when you go into the Fourier domain, you're working in this shifted space. You have to keep that in mind at all times. When you go into the Fourier domain, you're in a shifted space. Everything you do has to be then thought about in that shifted space. Okay? All right. Very impressive, I know.
And you're saying that this FFT flips the sign of half coefficients, it doesn't unflip them?
That's right. Yeah.
And if they're complex, is it like the complex conjugate or what?
Yeah, so if I took a complex thing, then I'd get complex pieces. And here's another problem. Yeah, in fact, most of the time, when you do this, and it didn't do it here because it's such a simple function, but if you take a Fourier transform, what was the kernel? Do you guys remember the kernel? E to the I kx. Well, turns out when you do this thing, all the coefficients, in theory, are supposed to be real, actually, for this function. But what does numerical roundoff do? Typically, it says, well, okay, I'm going to give you a 10 to the -16th imaginary component. So anytime you usually work with FFTs back and forth, you pick up numerical roundoff. I saw Leah move, so you can see. And I'm going to hide again. Sorry, I was playing games in class. I shouldn't do that.
I'm sorry,
yeah.
So every other real coefficient is split. Is it true that every, like if it's
Yeah,
A plus
multiply
BI,
by -1.
every other one?
Every other one.
Okay.
That's it. Okay, so that's the basic thing. That